Hey everyone, today we're going to be covering section 7.1 day 2. This is going to be about differential equations and something we call slope fields. So differential equations we've already worked with quite a bit. We know to recognize them because we'll see dy dx set equal to some function. Now, we know if this is just in terms of x, then we're going to have just a basic differential equation. Or if on the right we have it in terms of x and y, that's going to be our separable differential equations. And we'll have an opportunity today, I think, to review that a little bit. But mostly we're going to talk about something called slope fields. And what these are going to do is going to help us to graph a differential equation, or graph the solution to a differential equation. So when we're solving differential equations, we know there are infinite solutions, right? Because we know we always put the plus c at the end. Okay, so this is why we need an initial value in order to solve for a particular solution. So if we're given an initial value, then we're able to solve for c and get that particular solution. Now, when drawing the graph of differential equations, we need a way to represent that there are infinite solutions, but it should also show that the graphs of those solutions follow a prescribed behavior. So let's go ahead and look at an example of one. So first I'm going to do this the way we already know how. So, sorry about all the shaking here. It says to graph the family of functions that solve the differential equation dy dx equals cosine of x. Now this one happens to be really straightforward, so I'm just going to use this as a quick opportunity to review solving a differential equations. So if we have dy dx equals cosine of x. Again, I can recognize it's a differential equation by the dy dx. We know the first thing we're going to do is multiply by dx. So we're going to have all the y's on one side and all the x's on the other. Then we're going to go ahead and integrate. Well, the integral of dy is just y. My antiderivative of cosine x is sine of x. And then we're going to put, there's our plus c. Okay, so in reality, if we think about this, we could have a whole bunch of equations that are solutions to this differential equation. This c is a constant, so we could have y equals sine of x plus 0. We could have y equals sine of x plus 1. We could have y equals sine of x minus 1, right? We could go on and on. And so if we went to graph this family of differential equations, we would just be graphing this sine function, and this plus c is just representing a shift. Right? We know this plus c is just a vertical shift. So my sine of x plus 0, that's my regular sine curve. So sine of 0 is 0. Pi over 2 is 1. Pi is 0, 3 pi over 2. So I'm going to draw hopefully an okay looking sine curve here. Okay, and then I could keep going. So I know, let's see, I have sine of x plus 1. That's just shifting all these points up 1. So there's my sine of x plus 1. Okay, and then sine of x minus 1. Start from our standard, and we're going to shift it down 1. Okay, and so we could keep going. We could fill this all up with all of these sine curves that just have these vertical shifts. Now, here's where slope fields come in. We are going to be able to graph this family of functions without actually anti-differentiating. And here's how it's going to work. I'm going to take our same differential equation, see, dy dx equals cosine of x. And so I know my differential equation just depends on x. So I'm going to make a table here of my x value, and then I'm going to use that to calculate dy dx. Now remember, dy dx is a slope. We know that derivatives are the slope of a tangent at a particular point. So let's see, if I plug in, let's start over here, negative 2 pi for my x. I know that cosine of negative 2 pi is going to be a positive 1. So that tells me when x is negative 2 pi, my slope is 1. So what we do is at negative 2 pi, we just sketch in a slope of positive 1 everywhere x is 2 pi. And you can see on these three curves that we sketched in, that matches the behavior, right? If we think of very close to that point, it matches the behavior of those graphs. So let's keep going. Let's look at negative 3 pi over 2. Now, the cosine of negative 3 pi over 2 is going to be 0. So when x is negative 3 pi over 2, my slope is 0. And so you can see here we have these horizontal tangents which match our slope being 0. Now I'm going to go to negative pi. Let's see, cosine of negative pi is going to be a negative 1. So where x is negative pi, I'm going to sketch in a slope of negative 1. And you can see again, it matches the behavior of my solution. And so we could keep going. So negative pi over 2, cosine is going to be 0. Everywhere x is negative pi over 2, I'm going to sketch in a slope of 0. Okay, so that's the idea behind a slope field. We're just using what we know about the slope, which is given to us by our differential equation, to sketch a graph for what the family of functions would look like. And again, those functions are all solutions to that differential equation. So we'll leave this example here, and now let's go ahead and look at some other slope fields. Okay, so our new vocabulary. So suppose we want to produce the family of curves without solving the differential equation. So just like we started doing with the purple, we started sketching in that family of curves here, and it didn't require any knowledge of that actual solution. We just were working with what we knew about slope. Okay, so that's the idea here. So we want to produce that family of curves without solving the equation. Since dy dx tells us about the slope of the graph, we can use that information to draw a small piece of the graph at that point, which helps us determine the shape of the original function y. And so when we put together all the little tiny pieces, that is what we call our slope field. And so that's what we're going to work on putting together in these next couple of examples. All right, so let's go ahead and take a look. Now, I'm going to show kind of the long way of how we would go about this. Eventually, you'll get comfortable with this and probably won't need to show as much work, but I just want to be sure everyone understands where these values are coming from. So I'm just going to find the slope field at the dots here, the places, the coordinates indicated on my coordinate plane here. So I'm going to make a little chart, right? And I'm going to have my point. Now here, our differential equation depends on x and y, so we have to take both of those into account. And then we're going to use that to calculate our slope, dy dx. So let's go ahead and start at the point, let's do negative 1, 0. Actually, let's avoid that for right now. Let's start at negative 2, 2. Okay, so we're going to look at negative 2, 2. So if I plug that in, it tells me to take the opposite. X is negative 2 and y is 2. So the opposite of negative 1 is just going to give us a positive 1. So at negative 2, 2, I'm just going to draw in a slope that looks like it has a slope of 1. What's most important is that it's positive. Most often in the rubrics for AP, they're going to be checking if you have positive, negative, or 0 slopes as appropriate. Okay, let's look at negative 1, 2. So now I have the opposite. My x is negative 1 and my y is 2. So the opposite of negative 1/2 is a positive 1/2. Now when I draw this in, again, I said the most important thing is that it's positive, but I do like to make it a little flatter to represent that slope of 1/2. Okay, now my point 0, 2. So I have the opposite. Now my x is 0, my y is y is 2, and so that's going to give me a slope of 0. So I indicate that piece there. Okay, we'll finish off kind of this top row here. My next point is 1, 2. So over here I have opposite of positive 1 over 2, so a negative 1/2. So now this needs to be negative, and again, I'm going to make it a little bit flat. It's going to look something like that. And then I have 2, 2. So the opposite of 2 over 2, which is going to give me negative 1. So that's how we put together, kind of piece together these slope fields. Now, I like to look for anywhere I can kind of see a pattern that's going to knock out a bunch of points at once. So we can certainly go through all of these points and plug it in, and for some of them we'll have to. But what I notice here is that if x is 0, I'm going to make a note. If x is equal to 0, then no matter what y is, I have 0 over a number, I know my slope, dy dx, is going to be equal to 0. So what that allows me to do is I know x is 0 along the y-axis, so I can just plug in 0 slopes for those values. Now, similarly, if y equals 0, now I have a 0 in the denominator. I know dy dx is undefined. So I will typically mark that with just a vertical line here, because I know those vertical lines have an undefined slope. So at least then we're able to knock out a whole set of points just by uncovering some patterns. All right, now I'm not going to write this out necessarily, but let's go ahead and fill in the rest. So now I have negative 2 and a positive 1. So that's going to give me opposite of negative 2 is a positive 2 over 1 is a positive 2. So I'll make this a little steeper. Negative 1, so I have opposite of negative 1 over 1 gives me a positive 1. Now I have 1, 1. So the opposite of positive 1 is negative 1. Divided by 1 is a negative 1. 2, 1, I'm going to have a negative 2. Okay, at this point, it would probably be a good idea for you to try to fill in the rest. Maybe pause the video and then go ahead and see if we match. So I'm going to pause it and just fill in the rest. I think you guys have probably got the idea at this point, and then you could check with what I've got. Okay, so here's what the rest of that slope field should look like. And again, the actual exact slope obviously is not as important, but just definitely make sure you have positive slopes where you should, negative slopes where you should, and 0 in the correct place. All right, let's try one more before we move on. Sorry, this is going to require a bit of shifting here. Bear with me for a second. All right, so now we have the differential equation dy dx equals x minus y. So again, rather than making that table, I'm going to try and figure out any kind of patterns I notice. So the first thing I notice is that if x is equal to y, then I know that dy dx is just going to be equal to 0. So anywhere that x is equal to y, so along this line y equals x, I'm going to make slopes of 0. Okay. Now, the next thing I'm going to do is I'm going to work along, let's take our x-axis here. Okay, so now along the x-axis, I know y is 0. So if I'm looking at the point 1, 0, I know that's going to have a slope of positive 1. 2, 0 is going to have a slope of positive 2. Here I have negative 1 minus 0 gives me a slope of negative 1. Negative 2 minus 0 gives me a negative 2. Okay, and then I can work along the y-axis. Now I know x is 0. So here if I have y is 1, I have 0 minus 1 gives me a negative 1. Now I have 0 minus 2 is a negative 2. Now down here my x is still 0. Now I have 0 minus a negative 1. That's going to be a slope of positive 1. And then 0 minus a negative 2 gives me a slope of positive 2. And now to fill in the rest, I'm just going to kind of go point by point. So if I have x is 1 and y is 2, 1 minus 2 gives me a slope of negative 1. Here I have x is 2 and y is 1, so 2 minus 1 gives me a slope of positive 1. Over here, for negative 1 comma 1, negative 1 minus 1 gives me a slope of negative 2. Negative 1 minus 2 gives me a slope of negative 3. Now here, negative 2 comma 1, so negative 2 minus 1 is a negative 3. Negative 2, 2 gives me negative 2 minus 2 is a negative 4. And again, I'm going to go ahead and just fill this in without necessarily talking through it. And you could check yours with what I have. So that would be our completed slope field. All right. On the next page, we're going to look at a few more aspects of this and one kind of typical AP question you might see with this. So here's the first piece. Now, they've provided in this case the slope field, so they've given you the solution or the graph of the solutions to a differential equation. And what they may ask you to do is to sketch the path of the unique solution if the graph passes through 0, 1. So in other words, if we could solve the differential equation with this initial value, what would that graph look like? So the place to start here is we want to find the point 0, 1. And I know it's hard to see here, but it looks like that point is right here. I can kind of see a tick mark here. So there's my point 0, 1. All they want to know, if you can do, is can you kind of follow the trend here in this slope field? So I know if I'm starting here, my trend should be to go up here. And on this side, it should kind of be coming down and flattening out. So my solution might look something like that. Now, we're never going to get this exact, but again, the idea is can you kind of follow what's happening with that slope field? Again, if I wanted now to do this for 0, negative 1, I would find that point. It looks like it's right here. So again, now as I go off to the left, I'm kind of coming up and flattening out, and down here, I'm kind of following these curves. So again, don't get hung up on the exact location. Just being able to follow that pattern will be enough. All right, last piece here. Again, this is taken from a typical AP question, an FRQ. A lot of times you'll see slope fields and separable differential equations kind of lumped together in an FRQ. So they're giving us our differential equation here. This would be a separable differential equation. So the first part, they're just asking you to sketch that slope field. Okay? And so it's just for the 12 points that they have here. So these 9 and then along the x-axis. Okay, so we're going to do that just like we've been doing so far. Now, again, I noticed that wherever x is 0, my slope field, my slope is going to have a value of 0. So right away, I'm going to make these values 0. And so that's nice because I've knocked out 4 of my points already. So I'm going to make a note. If x equals 0, then dy dx equals 0. The other thing I notice right away is that if y equals 2, that's going to give this factor a value of 0. So then I know my slope field will also, or my slope, excuse me, will have a value of 0. So wherever y is 2, we make that 0. And now we're down to just 6 points. So let's go ahead and check this out. So when my point 1, 3, and again, if it helps you, you can go ahead and make a quick table just to organize this a little more explicitly. So let's say my point is 1, 3. I know that 1 to the 4th is 1, times 3 minus 2 is 1. That gives me a value of 1 for that point. Let's see, at 1, 1, again 1 to the 4th is 1. Now I have 1 minus 2 is a negative 1. So I'm going to have a negative 1 here. And let's see, now I have the point 1, 0. So I have 1. 0 minus 2 is a negative 2. So that's going to be a negative 2. All right, now I have negative 1, 3. Well, negative 1 to the 4th is still positive. So positive 1 times 3 minus 2 is 1. So that's a positive 1. Negative 1, 1. Again, my negative 1 to the 4th is still a positive 1. 1 minus 2 is a negative 1, so that's going to be a negative 1 there. And again, at negative 1, 0, I'm going to have 1 times a negative 2, which is a negative 2. So for part A, that's my slope field. All right, the last piece then says, while the slope field in part A is drawn at only 12 points, it's defined at every point in the xy plane. So essentially, we could expand this out and create this slope field for an infinite amount of points. Now it's going to ask you to describe all points in the xy plane for which the slopes are negative. So now there's a couple ways to think of this. The first thing I always do is I look at my slope field here, and I can see they're negative at these values. Now, if I look algebraically, I know this factor here is always going to be positive because it's to the 4th power. Now, this is only going to be negative if y is less than 2. So I know the slopes are negative for y that is less than 2. Now, we have to be careful because it's y is less than 2, however, unless our x is equal to 0. So we have to exclude, so values y less than 2 where x is not equal to 0. We want to exclude those values because we know there the slope's actually going to be 0. All right, so that's pretty much everything you need to know about slope fields. Tomorrow you get some practice with creating them and again addressing more of these FRQ type questions. Thanks for hanging in with a slightly longer video today.